Hi there, welcome to this video. My name's John. In this video we're going to be taking a look at something that I find particularly interesting in mathematics, which is the real numbers. Okay, so we're going to be having a look in this video at what do we mean by real number? What are the real numbers? So I'm not so much interested in what are the properties in terms of the behaviours of real numbers. It's really what exactly are we talking about when we talk about real numbers, because it's easy to think that we know what real numbers are until we're in a situation where we really have to explain what they are in a precise sense that's appropriate to mathematics, in which case we often realise that we don't really have much of a clue how to properly define real numbers. At A level, you've probably come across the set of real numbers, and you may or may not have spent some time thinking about what do we mean by this? What do we mean by real numbers, and so on and so forth. Maybe you just kind of take it for granted. I don't know. I probably did when I was doing my A-level maths. They crop up from time to time, or mention of them crops up from time to time. For example, when you're dealing with quadratics, you check the discriminant of a quadratic and it's less than 0, you might say, this quadratic has no real roots. Okay, and it can become a kind of just a conditioned reaction in some sense, and you don't necessarily think about what you're saying in too much detail. You just accept that's what you've got to say in some cases. Of course, those of you that are doing further maths or that have come across the system of complex numbers and imaginary numbers and things like that will be aware why you have to say that this quadratic has no real roots, because it still has roots. It's just that they're going to be complex or possibly imaginary. But if you have ever asked the question in your class, what are real numbers, depending on your teacher, you may have had a variety of different responses to this, but amongst them is probably a very wishy-washy kind of answer, which is something like, oh, real numbers are kind of like any number that you can think of, or kind of like any number that your calculator can display. Something like this, which is just completely inadequate as a response to this particular question, what are the real numbers? We really do need, at least in mathematics, a much more precise way, in contemporary mathematics at least, a much more precise way of understanding what we mean by real numbers. Now, the word real, when it comes to real numbers, has very little relevance in contemporary mathematics. The real numbers are no more real than any other type of number system that we might come up with. So the aforementioned complex numbers and imaginary numbers, the real numbers are no more real than these, and imaginary numbers are no less real than real numbers. By the way, I don't claim to have any final say what real numbers are necessarily, and I don't expect this video to give any definitive answer to the question, what are real numbers? All I hope in this video really is to give you a bit of an idea, if you have ever asked that question, or if you are interested in attempting to answer this question, the kinds of ways that you might go around about trying to answer it. Now, obviously, there's going to be a lot of detail that I'm going to have to miss out in this particular video. I expect this video to last probably between 30 minutes and 60 minutes, maybe, tops. So there's going to be a lot of detail that I'm going to have to miss out. So don't complain. If you would like me to go into more detail with some of the things that I maybe gloss over, just let me know in the comments section. And time permitting, further down the line, I'll hopefully get around to making a video that will go into more detail on that particular aspect. Okay, but I will not be giving a definitive answer to the question in this video, what are real numbers? Particularly in a philosophical sense, okay? Because it's impossible to answer that question. What are numbers in a philosophical sense? All we can do is try to answer this question from a mathematical perspective. How can we define them as purely logical, abstract entities? Because that's what the real numbers are in the contemporary view of real numbers. They are just a system of abstract objects that we call numbers that behave in a particular way. Okay, what these objects are in a philosophical sense is not something that a mathematician is necessarily going to be interested in. Really, mathematicians are going to be interested in how can we formulate these objects in a precise sense. What are their behaviors? How do they relate to each other? How do they relate to other objects? And how does this system as a whole relate to other objects? Things like this. Okay? But fundamentally, the real numbers are something that we create, and we impose behaviors and properties on this system of real numbers that we've created in such a way that it behaves, and the numbers behave in the way that we want them to behave. Okay, so we have objects within this system that we call numbers, and we can name them. We can call them 1, we can call them 2, we can call them the square root of 5, whatever, and we can combine them in a certain sense in particular ways, and we can call these methods of combination addition and multiplication, so that 1 plus 2 is equal to 3, 2 times 5 is equal to 10, and so on. Okay, it is possible to define other number systems where the objects are still called numbers, but they're understood in a different sense, and we might still have an addition and a multiplication, but it behaves in a different way. Nevertheless, the real number system is something that behaves in a very particular way that I've just kind of illustrated. 1 plus 2 equals 3, and so on and so forth. One of the main properties which really characterizes the real numbers and distinguishes it in many ways from many other number systems is the property of completeness. So this is not necessarily unique to the real numbers, but it is an important feature of the real numbers. And what the property of completeness effectively says is that there's no gaps in the real numbers, in the sense that every convergent sequence of real numbers converges to a real number. It doesn't converge to something outside of the real numbers. Maybe more accurately, I should say, every sequence of real numbers which has the Cauchy property converges to a real number. So what I mean by the Cauchy property, I'm not going to go into detail with this, but just so you know what the Cauchy property is, it effectively says that if we've got a sequence of real numbers, so I'll write it up here on the screen. So our sequence is A1, A2, A3, A4, and so on and so on. An infinite sequence of real numbers, that the distance between these real numbers gets arbitrarily close. As we get far enough along the sequence, the terms of the sequence get closer and closer in a sense. In a precise sense, what we mean by the Cauchy property, again, I'll write it up on the screen so you can see it. I'm not going to go into detail on this, and I'm certainly not in this video. Maybe I could make another video on this, but symbolically, and if any of you have done undergraduate, anybody watching this that's done any undergraduate mathematics, you will almost certainly have come across this symbolic definition. It's for all epsilon greater than 0. You get sick of hearing that, don't you, on undergraduate mathematics courses. For all epsilon greater than 0, there exists n, uppercase N, which is a natural number, so that for all n and m natural numbers greater than uppercase N, or greater than or equal to, it doesn't really make any difference, we have that the modulus of an minus am is less than epsilon. Okay, so like I say, I'm not going to go into detail with this in this particular video. If you would like me to go into more detail with this, just let me know. Note that we have in our numbers, in our real number system, we've got rational numbers and we've got irrational numbers. Now, if we excluded the irrational numbers from our real numbers and only had rational numbers, then there would be sequences of rational numbers which have this Cauchy property but do not converge to a rational number. In other words, they would converge to potentially something else. We would either say that they don't converge, or they converge to something outside of our system. So we have to include irrational numbers in our real number system to fill the gaps and to ensure this property of completeness. It's something that I'm going to talk about a little bit more later in the video. But aside from rational numbers and irrational numbers, we don't require any other type of number unless we start trying to solve certain equations, such as, for example, x squared plus 1 equals 0, in which case then we've got to spill out of the real numbers into complex and imaginary numbers. So what we know as the real number system is a fairly new creation. It's come about really in its modern form only in the last couple of hundred years. Many of the numbers that we now consider to be real numbers have not always been considered so. And even when they have been considered as real numbers, there's not necessarily been general agreement. Some people agreeing that they are real numbers, other people disagree. Now this seems unusual to contemporary mathematics, maybe, because after all the real numbers are something that we create. So what is and what is not a real number is really something for us to decide. But nevertheless, this might have been a much more sensible question seemingly to ask in past centuries, because the real numbers were considered to have some kind of reality. And again, the real numbers, as they were understood in history, even into the late 1700s, were not what we would necessarily consider real numbers now, how we would view the real numbers now. So numbers like 1, 2, 3, the counting, the positive integers at least, and the positive rational numbers would have seemed to have some kind of objective reality, and hence they were without a doubt real numbers. But even negative integers, negative numbers, weren't necessarily, it was questionable whether these were real numbers. And irrational numbers, absurds as they were called, it wasn't clear whether these were real numbers, because whether something was a real number was something to be discovered, as opposed to something that we just decide on. Okay, so for mathematicians in past centuries, it would have been something for them to attempt to discover whether these numbers were real numbers, irrational numbers, negative numbers, and so on and so forth. Nowadays, though, as I've already mentioned, we understand the real numbers to be a set of abstract objects, which we call numbers, although we don't necessarily go into the philosophy of what we mean by number and the ontological status of numbers and things like this. That's not for the mathematician to answer, that's for the philosopher to answer. But nevertheless, it is interesting, although frustrating if you do get into that kind of stuff. So in our real number system, as we understand it, we've got these numbers. We can classify them in various ways as rational, irrational. So each number in our real number system is exactly one of rational or irrational. There are no real numbers that are both rational and irrational, or neither rational nor irrational. Each number, maybe with the exception of 0, can be classified as either positive or negative. Exactly one of positive or negative, so no real number. With the exception of 0, possibly could be considered as being both positive and negative, or neither positive or negative. Now, we can take our set of real numbers as a self-evident totality if we wish. And we just say that this set of objects satisfies certain properties. We can combine objects in certain ways, in called addition and multiplication. And once we're happy that we have a system that works in the way that we want it to, we can get on with doing our mathematics, with finding out more about the system through further analysis and investigation. But to many, this is quite unsatisfactory. The structure of the real numbers is very complicated. And it seems to some, and I tend to agree, that the structure is too complicated to be taken for granted, and it really ought to be reducible to something simpler in some sense. And this something simpler is something that we can then build the system of real numbers up from. So, for example, it is possible, and I'm not going to go this far back in this video, but it is possible. In fact, I've done this in another video of mine, a video that I did on 1 + 1 = 2, defining natural numbers in terms of pure sets in the context of axiomatic set theory. And from these natural numbers, then we can go further and construct the set of real numbers. So the real numbers are quite literally nothing more than abstract logical entities. Now, in this video, I'm not going to go that far back. What I'm going to do in this video is show that the real numbers can be built up from the assumption that there is a set of objects called the natural numbers without defining in a logical sense necessarily, or a precise sense, what the natural numbers are. Okay, otherwise it's just going to take too long. And we set out with the assumption that there is this set of natural numbers that satisfies a certain set of properties, and I'm going to be referring to this book, by the way, through this video. So it's the Foundations of Analysis. I'm roughly going to follow the approach taken by Edmund Landau in this book. On the screen, I'm also going to have some screenshots that from this book, so you can see the pages that I'm referring to and things like that. We're going to take that as our starting point. The natural numbers, that we have those, we understand them. We're going to show, well, not from scratch, I'm not going to go on into all of the details, but we can show that they satisfy certain properties, and then we can define methods of combination, addition and multiplication, and then gradually build up to our real number system. Now, this is only one possible way that we can construct our real numbers. There's many different ways. The approach that Landau takes, there are many very similar approaches that differ slightly, that in slightly different ways, but kind of insignificant ways. Okay, so this is just one approach that we're going to be taking from Landau. So let's make a start. So let me scroll down. Because I've got the first page somewhere. Let me actually zoom out my computer. Okay, there we go. And right, here we go. So Foundations of Analysis. So this is a really interesting book. It's not particularly difficult necessarily, although if you're not familiar with the it's quite bare in its presentation. So what I mean by that is you get definitions, then you get a theorem, then you get a proof, then you get another theorem, then you get its proof, then you get another theorem and its proof, then you might get a couple more definitions, then you get a theorem, then you get a proof. There's sometimes some little explanations in between what's going to give you a bit of idea about what's going on, but mostly you're left to your own devices to really to think through what are the interpretations of these theorems and things like that. So it's not like a typical A-level textbook where you're given a formula and then you're given a zillion, gajillion examples of how to use this formula, and then you're given a bunch of examples a bunch of exercises where you have a go at using the formula yourself, and it's like this incremental progress that you're making throughout your course. It's much more rapid progress. It's a much more bare bones approach, but it's very typical. Once you get into higher level mathematics, it's very typical. But even if you are used to the style, the actual content, if you've never really considered exploring the nature of the real number system and things like that, and really getting into the nitty-gritty of numbers, then it can be a little bit overwhelming initially. But once you get used to it, it's a fairly straightforward book. You can probably download a copy off the internet if you want to have a look. So it's Foundations of Analysis by Edmund Landau. So what we start with is, if we get into things, where is it? Here we go. So we start with, naturally, chapter 1. We start with our set of real numbers. Okay, so we assume the following to be given: a set, a totality of objects called the natural numbers, possessing the properties to be listed below, which are called axioms, which we'll talk about in a second. And we've also got a notion of equality, a basic notion of equality, and also a basic notion of difference or non-equality, not equal to. Okay, and equality has to satisfy these properties 1, 2, and 3, which are called reflexivity, transitivity, and I've missed one out. I can't remember, but it's effectively saying that equality is an equivalence relation. Okay, so that's what we start with. That's our basic material. So we're taking the natural numbers as something that we already understand as existing in some sense. So the properties that the natural numbers have to satisfy are axiom 1, that 1 is a natural number. So we have an object that we call 1, and it is a natural number. For each natural number, there exists one natural number called its successor, denoted by x prime. That's axiom 2. There's no notion of addition yet. We don't know what we mean by addition just yet. Axiom 3, we always have that the successor of x is not equal to 1. So effectively there is a first number and it is 1. And then axiom 4, if the successor of x and the successor of y are equal, then x and y are equal. And there's axiom 5, which I've actually managed to cut off here, which is the axiom of induction, which is a bit more complicated than the other axioms. Actually, maybe it's best that I cut it off anyway. But there is a 5th axiom called the axiom of induction, which is, if any of you have come across proof by induction that are watching this video, then it's kind of based on that kind of idea. That if something is true, a certain statement is true for n equals 1, and you can show that if it's true for n equals k, that this implies that the statement is true for n equals k plus 1, then the statement is true for all positive integers greater than or equal to 1. This is kind of considered to be a fundamental property of the natural numbers, the inductive property. So we don't really need to, it's not a big part of what we've got going on here. So I won't worry too much about it. So once we've got our natural numbers, the next couple of chapters in Landau go through defining order on, actually first of all it's addition. So Landau defines addition, what we mean by addition of natural numbers, then sets an order on the natural numbers. So understand that the natural numbers as they're initially given to us as this basic set has no order on it. It's just a set of objects called numbers. Okay? It's not till further down the line that we have a specific order imposed on on that set. And then Landau goes on to define multiplication. And in this way we can show that this set of natural numbers behaves in the way that we expect it to. Okay, so we have things like 1 plus 1 equals 2, 1 plus 2 equals 3, 2 times 3 equals 6, and so on. Okay, notice also that 0 hasn't made an appearance yet. Okay, maybe some authors, some books will consider 0 as a natural number, and there's nothing wrong with this. It's just that Landau doesn't do it. There's no necessity for 0 to be considered as a natural number. really doesn't make any difference whether you do or you don't, but Landau does not. Okay, but there are versions of Landau's construction of the real numbers that will assume that 0 is a natural number, and it doesn't really substantially change the overall argument. So, from the natural numbers, we can go on to form what are called the fractions. Okay, so fractions are pairs of natural numbers, but we write them in a particular way. Okay, x1 over x2. So we've got two natural numbers, x1 and x2. Our fractions are written as you might expect them, x1 over x2. There's no necessity for this. We could literally just think of fractions as a pair of numbers, x1, x2, almost like a pair of coordinates. In fact, sometimes rational numbers are considered as pairs of coordinates. But Landau here chooses to write them as fractions are typically written. And we've got a notion of equivalence of fractions. So not equality, but equivalence of fractions. And that's given in definition 8 here. So what does it mean for two fractions to be equivalent? It means that, so if we've got x1 over x2, y1 over y2, these two fractions will be equivalent if x1 times y2 is equal to y1 times x2. Which makes sense. For example, if we think about normal fractions, for example, I don't know, 5/15 and 1/3, for example. So x1 here is 5, x2 is 15, y1 is equal to 1, y2 is equal to 3. Then we can see, for example, that x1 times y2 is equal to 15, and x2 times y1, or y1 times x2, is also equal to 15. So because we've got equality, then we can say that 5 over 15 is equivalent to 1/3. And notice that equivalence is written with this little tilde kind of symbol, whatever it's called, rather than equality or something like that. So once we've got the fractions, we can impose a certain structure on the fractions. We can define a suitable way of adding fractions, multiplying fractions. We can place an order on fractions so that they work in the way that we expect them to do. Okay? And then once we've done that, we can go on to... So I'm going to be going quite quickly through this. I'm going to be missing out a lot of detail. If you do want the full details of this, I recommend that you get Landau's book and you have a look through it yourself. But I am going to have to miss out a lot of detail. But having said that, if you hop over to my other YouTube channel, The Second Number Class, there you can find much more detailed videos on Landau's work. I've got a series of videos where I go through a lot of the contents from Landau's book. Not everything line by line, but I go through in much more detail the contents of Landau's book. So even if you don't have the book available to you, you can get a good idea of what's there if you watch those videos. That's my other YouTube channel, The Second Number Class. I'll leave a link in the description to this video so you can get there. So once we've got that, we can move on to what are called the rational numbers and the integers. Okay, so rational numbers, often we equate rational number and fraction, or we think of these as being synonymous. Now we have to distinguish them here. Fractions and rational numbers are going to be two different things to us. Okay, fractions are what we've been talking about with pairs of natural numbers. But the fractions 5/15 and 1/3, these are two different fractions. But they correspond to the same rational number. Okay, so we form the rational numbers by taking all of those equivalent fractions. Using our definition of equivalence of fractions, we gather together all the fractions that are equivalent into a new set. Okay, so we take the fractions 1/3, 2/6, 3/9, 4/12, 5/15, and so on and so on and so on. We gather all of these together and we jam them into a single set, and we call this a rational number. So a rational number is a set of equivalent fractions. Okay, that's what we've got here in definition 16. By a rational number, we mean the set of all fractions which are equivalent to some fixed fraction. Okay, so the symbols uppercase X and Y and Z are typically used to represent our rational numbers. We also have some rational numbers, some fractions, for example, that look like the following maybe. So we can take, for example, 4/1. Okay, and this is obviously equivalent to 8/2 and 12/3 and so on and so forth. There is a rational number that corresponds to the fraction 4/1. And because of the specific form of this fraction, 4/1, namely that it's got a 1 in the denominator, we refer to the rational number that we form from this set of fractions that are equivalent to 4/1 an integer. Okay? It's still a rational number, but it's a particular type of rational number called an integer. So within our rational numbers, we have a set that we call integers, which are rational numbers that corresponds to sets of fractions that are equivalent to fractions of the form x/1. Okay. Hope this is making sense. Like I say, if there's anything that you're not sure about, that you want me to go into more detail about, just let me know. Because some of this, because I am going quite quickly through this, there is a good chance that it's not necessarily going to make too much sense if you haven't come across this kind of stuff before. But just to give you a bit of an idea about what's going on. So we've got our rational numbers and integers, and that's all well and good, but what's the purpose of this? Where is this going? Well, this is where we start to realize where this is going now, because what we can do once we've got our rational numbers and we have these integers, once we've got the rational numbers and we've set them up in a particular way so that we can add them together in a way that addition works in the way that we expect it to work, we can multiply them in a way that seems to make sense. So multiplication of rational numbers works in, again, the way that we expect it to. But also the integers work in a certain way. In fact, the integers work in exactly the same way as the natural numbers that we started with. So once we've got all of our rational numbers, we have a subset of those rational numbers, the integers, that behave just like the natural numbers. So what we may as well do now is get rid of the natural numbers that we started with and actually bring in this new set, this set of rational numbers, which is a richer set. It's a much more expansive set. And there's a subset in there that behaves just like the natural numbers that we started with. Okay, the behaviours mirror each other exactly. So we're throwing out this set of natural numbers and replacing it with something that's much more that's got much more structure to it. Okay, can you see where this is kind of gonna go? If not, don't worry, we're gonna get there. So we've got our set of rational numbers now, and they do what we expect them to do. But we can't stop there, because the rational numbers are not the real numbers. We've got these gaps in the rational numbers that we somehow need to fill. And it's quite an ingenious way in which Landau wasn't the originator of this idea. Dedekind was one of the first to really come up with this idea, Richard Dedekind. Although I'm not sure that Dedekind was the first, necessarily. But the idea of cuts. Okay. So, a cut is a new structure. So whereas before we gathered up all of those fractions that were equivalent to a fixed fraction, stuck them all together in a new set. Well, now we're going to gather together sets of rational numbers in a particular way. So, definition 28, very important definition. A set of rational numbers is called a cut if there's three conditions that it has to satisfy. One, it contains a rational number, but does not contain all rational numbers. Every rational number of the set is smaller than every rational number not belonging to the set. And three, it does not contain the greatest rational number. Okay, so this is quite an abstract structure. These cuts are quite abstract things. And if I were you, if you've never come across this concept before, I'd spend some time trying to think about these. I wouldn't necessarily recommend it, but if you think about all of the rational numbers on a line, so remember we don't have 0 yet, but we can think about all of the other rational numbers. I don't necessarily encourage this because it gives the idea that we've already got something that's complete, that our real numbers are in some ways a line. Now it's just a visualization. Don't take it too literally. It can be a bit misleading. It is better if you can to think about these as purely as sets of rational numbers. But if you need to, maybe think about a kind of number line where you've got all of the rational numbers all in order, and you're kind of making a slice somewhere in the line, at particular places in the line, in such a way that you're creating two classes of numbers, or two sets of rational numbers. So you've got the rational numbers to the left of the line, the rational numbers to the right. There might even be one that you've actually cut through, a particular rational number that you've cut through, and see how the cutting in different places, how it will kind of correspond to this definition. I mean, it's a very simple visual thing. It can help you to get a clearer idea of what we mean by a cut. If you think about it in this way, but it can be a little bit misleading as well because it kind of suggests that we've already got the irrational numbers there, which we don't yet. So, just as before, we can force these cuts to have particular properties so that we can add them, we can multiply them, we can order them, and once we've got to these cuts, we've effectively constructed the positive real numbers. Okay? So what we can do at this stage is, again, we can throw out the old and bring in the new. So this set of rational numbers that we threw out the natural numbers, we brought in the rational numbers and the integers. Well, it turns out that within these cuts, there are certain cuts that behave exactly like the rational numbers. There are certain cuts that behave exactly like the integers and therefore exactly like the natural numbers that we started with. But there are also some more. There are some more cuts that don't correspond to the rational numbers. And there is one and only one cut that corresponds to each rational number. Okay? So we don't need to worry about two cuts corresponding to rational numbers or any rational numbers being missed out or anything like that. For each rational number, there is one cut and only one cut that corresponds to it, and every cut, every rational number corresponds to a one and only one cut. So, because of the behaviour of the cuts, we can get rid of the rational numbers and the integers and bring in this new set of things called the cuts, where we've got a subset that behaves just like the rational numbers. We call them rational cuts. They behave just like the rational numbers. We've also got a subset called the integral cuts that behave just like the integers, and in turn just like the natural numbers. But we've got this extra structure. We've got these bits in between, it turns out. These cuts that don't correspond to any rational number or any integer. These are what we call the irrational numbers. Now, it goes into much more detail in Landau's book, these cuts, there is a substantial qualitative difference between the rational cuts and these other types of cuts. So there is a way of distinguishing them. And it's got something to do with when we separate the rational numbers into these two classes, we've got kind of a lower class and an upper class. If that upper class has a least element, then what we've got is a rational cut. The lower class never has a greatest element. But if the lower class never has a greatest element and the upper class never has a least element, or doesn't have a least element, should I say, then what we've got is it doesn't correspond to a rational cut. It's something else, and this is what we will call an irrational number. So for all intents and purposes, now we have our set of positive real numbers. So as you can see, the positive real numbers are effectively sets of let me get this right, sets of equivalent fractions, or sets of pairs of natural numbers. So it's quite a complicated structure that we've got here. These cuts that we're going to call real numbers, they're very complicated things. It's quite, maybe initially it's quite strange to think of numbers having this kind of internal structure to them. We kind of think of numbers as indivisible things, very simple indivisible things. But it turns out that when we construct real numbers in this way, they've got a very complicated internal structure. Now all that's left for us to do is to just complete the picture. So what we do now is to every cut, we associate another cut, we create another cut for each one of these cuts, that is basically the negative of that cut. So we're creating now the negative real numbers, and then just to finish things off, we need a 0. So we create a new object called 0. So putting all of these together, the positive cuts, each of these negative cuts, one of each, where there's a one-to-one correspondence between the positive and negative cuts, and 0, we put all of these together, then we've got our set of real numbers. And by imposing a certain structure onto this new set, we can get this structure to behave exactly like the real numbers that we've come to know and love. We can add them in the way that we expect. We can multiply them in the way that we expect. We can order them in the way that we expect, and so on and so forth. The final thing really with respect to real numbers that Landau does is... did I include it? Oh, sorry, there we go. So the real numbers, that just kind of clarifies what I've just said. The cuts will henceforth be called positive numbers. Similarly, what we've been calling rational numbers and integers will henceforth be called positive rational numbers and positive integers. We create a new number called 0, distinct from the positive numbers. We also create numbers which are distinct from the positive numbers, as well as distinct from 0, and which we call negative numbers. Okay? But then finally, the one property that we really want our real numbers to have is the property of completeness, and that's it's shown that this set that we've just formed, that we've just created, has this property through theorem 205, Dedekind's fundamental theorem. So let there be given any division of all real numbers into two classes with the following properties. There exists a number of the first class and also one of the second class. Every number of the first class is less than every number of the second class. Then there exists exactly one real number. I can't remember what that is in... I can't remember what symbol that is from the Greek alphabet. Such that every... I know it's not a H, but I'm going to say H anyway. Belongs to the first class, and every H greater than this weird symbol that I can't remember to the second class, and so on and so forth. I can't remember my Greek alphabet. So this completes the picture. This gives us a system of abstract objects that have a very complicated internal structure to them, nevertheless, but which behave in exactly the way that we want them to behave. Okay? And that's it. That's how we can think of the real numbers. So when we mean real numbers, what do we mean? Well, one way that we can think about it is as sets of pairs of natural numbers with a certain structure built around them. Okay, that's what we mean by real numbers. Oh, that's what we can mean by real numbers. Now, there's all sorts of different ways that the real numbers can be constructed. This is not the only way. There's all sorts of ways. But even when we've got to this stage, we still don't have all of the answers about the real numbers. There's still the structure of the set of real numbers is so complicated. There's still so many unanswered questions and unsolved problems relating to the real numbers. And one particular question that currently has no definitive answer is, how many real numbers are there? Now, this might seem like a strange question, and we might naively say that there's an infinite number. Obviously, there's an infinite number of real numbers. But the question is much more subtle than it may first seem. And thus it demands a much more subtle response, particularly in light of George Cantor's transfinite numbers. Okay, again, if you want to know more about George Cantor's transfinite numbers, hop over to my other YouTube channel. It's the second number class. You can find out more about that kind of stuff over there. But George Cantor developed a theory of transfinite numbers where there's different levels of infinity, different sizes of infinity, and so on and so forth. So it doesn't suffice to say this is infinite in size, this set has an infinite size or an infinite number of members. What we really want to know is what order of infinity. It's too vague to say it's just infinite. Nevertheless, some mathematicians in the past, amongst them L.E.J. Brouwer, would say that such a question is meaningless, has no sense to ask how many real numbers are there. But nevertheless, attempts to answer this question have resulted in many of the very, very, very deep developments in mathematics and logic during the early 20th century, early to mid 20th century, and on from that as well. There's still ongoing research into some of these ideas, but really it culminated in Paul Cohen's, Kurt Gödel's and Paul Cohen's discoveries or theorems or whatever you want to call them, because it turns out that the current mathematics system of mathematics that we use is not powerful enough to answer this question. It's too weak to answer this question. Maybe in future we'll do mathematics in a different way, in a completely different way that will either make the question redundant as to how many real numbers there are, or will produce a definitive answer. But unfortunately, our current axiomatic foundations for mathematics is not a powerful enough technique, powerful enough system to answer the question definitively, how many real numbers are there? So what I've discussed in this video is the kind of typical understanding of real number, or one of the typical understandings of real number in contemporary mathematics. And it's not to suggest that there's not other ways of understanding what real numbers can be or how they can be interpreted. It's common in, for example, it's common in contemporary mathematics to use the aforementioned Cauchy property to define real numbers as equivalence classes of sequences of rational numbers, which I'm not going to go into in this video. But Landau's approach constructs the individual real numbers and then forms the continuum of real numbers from them. So we're thinking about the continuum, the set of real numbers, as these kind of individual points, so to speak. But other authors may take the view that the continuum has priority. The continuum of real numbers has priority. Different philosophies of mathematics produce different interpretations of mathematics, and Brouwer, who I've already mentioned, is often associated with a school of thought in mathematics called intuitionism, And the intuitionist approach to mathematics was never generally accepted, although Brouwer was a first-rate mathematician, very, very talented, very influential mathematician. But to the intuitionist, questions about real numbers become questions about infinite sequences of integers generated through a succession of arbitrary choices, or choice sequences. And I'm not going to elaborate on this idea any further in this video. It's quite a complicated idea and how it works and everything. Maybe I'll do that in another video. But nevertheless, I hope that I've given you some food for thought. I don't expect that I've given a definitive answer as to what the real numbers are. I hope not, because that wasn't the aim of the video. But hopefully this will give you some ideas about things that you might want to read up on further, or if there is anything that you want to ask about the real numbers, feel free to ask me in the comments section or get in touch. I'd be more than happy to help you out. But I think that's everything that I'm going to say about real numbers in this video. I hope you found something useful in here, and I will look forward to seeing you in the next video. Thanks very much for watching.